Maybe you can start recording. Thanks. So today, Nikita is going to present us the homework number 2, the Grassmannian length calculation. And it's supposed to be used to estimate the non-linearity of the neural network. I'm still curious how that actually works, but maybe we can figure it out. Okay, it's yours.
All right, thank you. I'm not sure I can fully answer this core question today, but I think we will try to approximate the answer at least. So let me share the screen now. Okay, please tell me if you can see the notebook.
Yes.
Awesome. Okay, so this Grassmannian length, the idea here is that we'd like to have a way to look at to look at what the neural network is doing as a curve. So we'd like to imagine that what the neural network does is that it changes some input, and we can think of that of changing that input as a curve. If you read this prompt from the task, we can define a curve as this mapping from one real scalar value to Rn space. So basically to a coordinate, for example. And this is basically, this comes from physics, I think, the parameterization of the curve, or Riemannian geometry, where we have one coordinate, which you can think of as time, time t, and you get the position in space. So if you start somewhere here at t0, we have this coordinate, let's say x0, y minus 1, and then at t a little bit further, we have a different x, a different y. And you can have these curves in different dimensions with more axes than just x and y. And this is just a general way to define any curve. So we can think of what the neural network does as sort of changing the input in the same way, right? We have some input. So this is not totally clear to me though, because in a neural network, we never have one-dimensional input. But we can figure it out later. The idea with the curves though, just without not thinking about neural networks for now, is that they have some features which we can analyze that they will later transfer to neural networks. So first off is the velocity. So the velocity is simply the derivatives of this curve of this function x at each point. So I guess it's also familiar from physics to many of you that if you take a derivative of the position, you get the speed or velocity. So this is the same thing. We get these velocity vectors, which show the direction of where we are going right now on the curve and the magnitude of basically how quickly we're going there. This is useful because we can kind of then like see how we move around the curve. And what we can do later with this is to take this Gauss map and basically map using the derivative, the velocity, the original curve into what's called a Grassmannian. So the formula for that is that we take the velocity of the curve and we normalize it. So basically we get rid of this magnitude, so all the magnitudes become the same, and we reposition them so that everything starts at 0. In the end, we get this unit circle, and you can think of it as like each vector here came from here, and I guess the more If the curve has more lines, more tangents in one direction, then it will be more prominent on this unit circle. And still, although it's a unit circle, it's still a curve in a way. It's kind of hard for me to think about it this way, but if you think about it, it's still the same thing. We get t as input here, and we get the output, a coordinate, like x and y in this case. So it is still a curve. And for this curve, we can calculate its length. And that would be the Grassmannian length. So let's back off a little bit and just think about the length of any curve. So we have this curve, for example. From calculus class, they say that they hope we learned how to measure the length of the curve. I didn't, but it kind of makes sense. So we take an integral of the norms of the derivatives of the velocities at each point. So basically, these velocities, remember, it's just the derivatives. And if we take the norm, it's just the size, the little sizes of the little chunks. So you know, derivatives are like chunks, and like we can think of them as infinitesimally small chunks of the function. And if we take the norm of that, it's basically the length of those chunks. And then we basically sum them up across the whole curve. And that's how we get the length of the curve. And then the whole idea of Grassmannian length is that we apply this, we calculate this length not on the original curve, but on these transformed curve known as Grassmannian or the Gauss map. And just to remind you how we got here, we took the derivatives and normalized them. So basically, the whole thing is pretty simple in terms of how to mathematically calculate it. It's also pretty similar in code, as I'll show you later. But in terms of, I guess the trickiest question is how exactly, like, and why does it show the nonlinearity? And how does it apply to neural networks? And for that, I have some ideas, have some links. I don't have a clear-cut answer that would make me feel fully comfortable. So I think we'll have, it'd be cool to have a discussion on that. So let's start with task A. Here, we'd like to just make a, as they say, a sanity check. Make sense. Make sure that the Grassmannian length even makes sense to calculate, as this notion of how do they say it? Basically, as a notion of curviness. And for that, let's check that if we rescale the original curve, like this curve, if we just make it twice as big, for example, that the Grassmannian length stays the same. So we define a new curve y of theta as scaled x theta by alpha. And we want to prove, or they say informally show, that the Grassmannian length of this new curve equals the original curve that's not scaled. So the intuition
I have a question here.
Yep.
It doesn't seem to be immediately evident to me why, when you scale the original curve, that the length of the, not the length of the curve, the curviness of the curve stays the same. Do you have any comment about that? So
yeah,
let's say
if you think
you scale
about
it bigger.
Mm-hmm.
Go on.
Yeah, like by curviness here, what I mean is it's basically like scale invariance comes in with it. Like, just imagine if you scale this by 2 and then go away from it twice as far as you were before. It will look the same way, right?
Yes.
So it will be the same curvature. Like, the angles between certain positions. If we take this position and take this position, the angle here would be the same. That's, I guess, the idea. And I mean, that's intuitively. I can, like, we can show it mathematically. But I don't know, is my intuition helpful for you or not?
Yes, I think the explanation that the angle between 2 points stays the same, that seems to make sense.
Mathematically, the curvature has to do with the second derivative, so to say. And when you just scale the curve, basically you don't change the second derivatives. If a point was about to go over this curve and you only scale it, you change the speed, but you don't change the curvature, which has to do with the rotation of this tangent vector, which is also related to these angles that he mentioned, that the angles will remain the same. So in principle, by a linear scaling of the curve, you don't change the curvature of the curve, only rescale it. And as he said, the angles are preserved, and because the second derivative is not changed at all.
Mm-hmm. I think that's a better way to show it, Raul. Thank you. The way I showed it is not by taking the second derivative, but just by playing with basically, if you take a look at what Grassmannian length is made of, it's again the Gauss map, and then we take the length of that Gauss map. If we plug in alpha there, when we take the first derivative, when we calculate the velocities, velocities are derivatives of x, and we can take out the alpha from there. And then we can take the alpha from here as well. So the Gauss map would be the scaled velocities divided by the norm of scaled velocities. And there's this rule from like the property of the norm that we can take out a scalar value with a module, like with the absolute value. So we can take out this alpha divided by modulo alpha, absolute value of the alpha. And this is the Gauss map. But then when we compute the length of the Gauss map of this Grassmannian, then again, we apply the norm, and we can again take this scalar value out as an absolute value. And alpha divided by absolute value of alpha is either 1 or -1. And if we take the modulo, it's of course 1. So the term becomes again the original term without the scaling, and this is the same as the Grassmannian length of the unscaled version.
That seems to make sense.
I also like the way Raul showed it. You can also think of it just by you can do the same thing, show it mathematically by just taking a second derivative, the Hessian, and then I think the constant just becomes 1, right? So the first time you take a derivative of something with a constant, you take out the constant, but then it becomes 1, right?
No, I think the way you did it is the straight way. I was only answering about the notion of curvature, that it has to do with the second derivative. But the way to prove the exercise is exactly the direct calculation that you did. That's perfect.
All right.
Actually,
okay, does anyone have any more questions about this? No, yeah, Tambit.
I might have.
Mm-hmm.
So one thing that was misleading for me when I looked into this was that if you go back a little bit to the definition of the Gaussian map, the definition of the Gaussian map is that it's the first derivative divided by the norm of the first derivative.
Yeah.
Now, if you go down, and then there is a definition of the length of the curve.
Oh, yes.
And this uses also the first derivative, but you apply the first derivative to the Gaussian map, which was itself already first derivative.
Exactly.
So it's actually the second derivative. this
Exactly,
v
yes.
here.
Yeah.
And I wonder if your derivation took it into account.
When I in the implementation part, yes. At first I didn't do that, and it was a bug. But then yes, it did take that into account. And here, yes, there is this derivative, but in the
Okay. I missed this little prime previously, but yeah.
Yeah, it's not very big. I should have probably used other notation, but you can see. Give me a second. I'll take a look at this. Yeah, so we're taking the derivative of this, right? What the length would be is the norm of the derivative of this thing, of this guy. So here is a scalar again. We can take it out, and oh yeah, that's what I did here. So the scalar would take it out, and since it's under the norm, we take it out with a absolute value. But yeah, this is
okay,
here is
we don't even
prime.
We don't even need to know what is the derivative of the v divided by the v norm of the v.
We do for calculation of the length, but not for showing. Like here, I just wanted to show that this thing is just one, and so we don't care about it.
Yeah. Yep.
Now, actually, that I think the prime there shouldn't be there. I think it doesn't change the result that with scaling the curve, the Grassmannian length is invariant. It doesn't change. But I think by the definition, if you go up, can you go up?
Yep. You mean to here?
Yes. So the length of a curve, yes, is the integral over the modulus of the speed, differential the parameter, and summing up all that with the integral. And then when we have the length of the Grassmannian, so the Grassmannian itself is computed with a velocity, and when you compute L, you should derivate again.
Yeah. If you don't do that, it will be.
Yes.
So
I guess yes. I guess yes. You have to derivate again. Yeah. Yes, I think it's right.
Yep.
Yeah.
Yeah, the way usually
Yes,
people define the length of the curve is also through like the norm of the derivatives, not just the norm of the values.
Yeah. So in this case,
the vectors themselves.
Yeah, it's like that. Yeah, yes.
So yeah, so you can think of it as this way, that we first take the derivatives to get the Grassmannian, and then when we compute the length of the Grassmannian, we again have to take the derivatives. So this makes us take it twice. Okay, does anybody have any more questions about this?
No.
All right, let's move on. Okay, for task B, I'm not as confident in that my response is so full here, but this one seems that the intuition holds up that easily here. But tell me what you think. Anyways, the question here is, what if we reparameterize the curve by changing basically changing the way how time flows? So there's a function now that maps t min, t max to theta min, theta max. And we reparameterize the curve so that it's not a function of t, but that it's a function of, not the function of theta, but the function of this t. And we want to still show that the Grassmannian length stays the same. So here, my intuition, there's a mathematical argument to be made, but let me get back to it later. The intuition is that by reparameterizing the time here, what we do is we basically change the speed of movement along the curve. We don't change the shape of the curve. We don't change its curvature. We just change how quickly go along this curve, because the start stays the same. T min, I mean, the start maps to a different value, but it's basically you can see it as either going slower or faster, or starting at a later point and finishing at a later point. You can stretch the time and squeeze the time, but you're not doing anything with the curve. Mathematically, I don't understand how to derive this myself, but there's this notion of if you take a line integral, the value of the integral would not depend on the curve parameterization. So I saw it here. Basically, it's the same definition of the curve. So it takes some input, and we get an R in N output. And then this is a line. So we get some line, and if we take the here, line integrals of vector fields are independent of parameterization. R is our time t in absolute value, but they do depend on its orientation. So orientation makes sense. If we change the way we go through time, maybe something will mess up, but we have this monotonically increasing function. So it means that it's not an arbitrary function. We still go forward in time. So this looks mathematically correct to me, although I'm not able to like formally describe it. I guess they're not asking for it, and my intuition is simply that changing time just basically changes the speed, the way of going along the curve, but not its shape or curvature. And I'm open to questions and your thoughts. What do you think, if that makes sense?
I was thinking about this myself, and to me it seems that if you take the derivative of the x with respect to t, then what happens is the result is the x prime at ft times f prime t, right? Like it's a derivative of the composite function. First you take the derivative of the x at the position ft, and then you multiply it with the derivative of f at the position of t.
Okay. And that sounds basically like scaling it.
And then once you plug it into the Gaussian map formula, then then you have the f prime t on top and on the bottom. And I was thinking that maybe they cancel out. Do they?
Maybe like we've showed in the first exercise about the rescaling, and we will get this rescaling when we will have the derivative of theta with respect to t, of reparameterization of.
And yes, and later we can switch like reparameterize the integral, that instead of doing the integral over t, we switch to doing integral over theta, and we change the bounds to be from t min to t max to theta min to theta max. And we can do this because f is monotonically increasing function. And so I have a like vague idea, but that it should work somehow like this. That you first take derivative of the x, and then the derivatives of the f cancel out, and then you can switch the variables from t to theta in the integral. I don't
I'm
know
not sure
if
that totally
somebody.
makes sense to me. Like I guess like it sounds correct, but I'm still confused somehow.
I'm a little bit concerned about this absolute value there, but you handled it well in the previous case. So I hope that it can be handled in this case as well.
Yeah, basically, I think you made a great point that it's basically going to be like multiplication of original curve by some value, and then we've dealt with scaling already.
Mm-hmm. Of course, it's not just scaling with constant. This time it's parameterized by the t, but this is the same value on the denominator and numerator, and these cancel out, and then you do the switch of the variables from t to theta.
Oh, okay. I see now where what do you mean by canceling out? You mean here,
Yeah, the
right?
same thing.
Because we have.
Yep.
Okay. Yeah, makes sense. Even if it's different, it's going to be the same for the same value of theta.
Yes.
Okay.
So I believe that like the same kind of derivation that you did above, it should be possible to do it here as well.
Mm-hmm. Yeah, that makes sense. Okay.
Okay.
Any more questions on this one? So the intuition again is just that if we reparameterize the curve, so we change how time flows, we still get the same Grassmannian length. So basically the curvature, how curvy, how complex, how nonlinear this curve is doesn't change.
But I think this should apply also to the original length of the curve, right? So it's not only the Grassmannian length that is invariant, but the usual length is invariant itself. Should be.
Yeah, even the original length should be invariant. That's true. Because yeah, like the only thing it's mapping is these t's to thetas, and t max should have the same position as theta max, and t min and theta min.
I think the length has to be the same because it's the monotonically increasing function, or maybe I'm simplifying too much.
At the end of the day, with length,
sure
what we are doing is integrating like small distances, right? So infinitesimal distances somehow, or speed vectors. And yeah, if the mapping is monotonically, at the end, as Mikita said, you're just changing the way you are driving on this curve, but then you pass by the same number of points, and the same length should be accumulated somehow. But if the mapping is not monotonic, what happens is that sometimes you go back in the curve. You go one direction and then you go back, and then you add extra length. So the mapping has to be monotonically. But I think that both, not only the Grassmannian, but the usual length also should be respected, should be invariant.
Mm-hmm.
Yeah, I think that way too. Although my thinking was kind of breaking when I thought of what if we take the derivative now? The derivative should change. But yeah, as you said,
yeah, you change the delta t in the integral also, so you change both, and then they compensate.
Yeah, that's true. Basically, yeah, our derivatives become smaller, but then our if we stretch if the new mapping is larger, right?
So yeah, because you have, imagine if your derivative becomes smaller, but you have more delta t's to integrate. So one compensates the other perfectly. All I'm saying, my point is that under this monotonic mapping, not only the Grassmannian length should be invariant, but the usual length of the original curve, that is also invariant.
Yeah, I agree with that. All right, then task C is the implementation part. Maybe before that, no, actually it's okay. Let's do it this way. So for the implementation, I couldn't run it in Jupyter, so I have it here in Colab. Basically, the authors of the course provide a starter with some code, not for the Grassmannian length, but the code for some curves, which define some curves, and so that we could compute their length, their Grassmannian lengths. And here I have those curves here. Plus, I added a circle because their tip is that a Grassmannian length of the circle should be 2 pi regardless of the radius. So there are some questions about like the Grassmannian length according to this code should be defined from some theta min to theta max, and that kind of makes sense because we have to take an integral from some theta min to theta max. So I guess we have to provide that when we calculate the length, and then it's kind of like it's not mentioned here for which length, like for which theta values the Grassmannian length of a circle should be 2 pi. But I thought that 2 pi is a good value, and for 2 pi, the Grassmannian length is indeed 2 pi. It's basically the full circle. We make the full circle, and then the Grassmannian length of a circle would be really a full circle. But anyways, to the implementation itself, remember what a Grassmannian length is. We take the derivatives to get velocities, we normalize them, and that becomes our Gauss map of the original curve. And then for that Gauss map, we calculate the length. So the way they suggested to structure the code is to have a function that takes a curve and returns its Gauss map, and another function that computes the length of any curve. And we can just apply it to take the length of this Gauss map. So I have here the Grassmannian length function. It takes the curve length of the Gauss map of the original curve. And Gauss map is defined. I have two versions. I'll explain why I have two later, and the curve length. So the simpler one is the curve length. It's simply what the formula says. We take the integral. This function is from SciPy. This is just an integral of the function that is norm of a derivative of the curve at t. And for the Gauss map, there's a thing to say. There's this thing I should discuss. So in the prompt, we were instructed that we'll probably use two calls to JAX JVP and one call to integrate. So what is JAX JVP? JVP is what we talked about it before. These are the Jacobian vector products. So remember, I think in I remember which lecture it was or which practice, but we were talking about reverse and forward modes auto differentiation, and they include these notions of Jacobians. When we do backprop in neural networks, we calculate derivatives, but derivatives for some functions like softmax are not just vectors. They are matrices, and these matrices are called Jacobians. But Jacobians could be really huge, so we don't calculate them directly, and instead we calculate these Jacobian vector products or vector Jacobian products. JAX just provides a great tutorial on what these mean and where they're used. I think by now I have some vague idea already by when you should use which and the intuitions, but not fully. I'll try to explain. So remember, there is forward mode auto differentiation and reverse mode auto differentiation. Reverse mode is the one we use in backprop. Here we have let me show you this. The difference is simply in which order we go through our derivatives in the chain rule. So in reverse mode, we have some derivatives. We show it as two derivatives multiplied, but then this one, dy by dw1, could be explained further, could be opened up further, and that's what we do. So we show it as itself, like we apply the chain rule there on the left, and we keep doing it. So we keep going back in time and taking the derivatives of functions we took a long time ago. In forward mode, we do the opposite. We start with the deepest, furthest in the path derivative, and we open up the following derivatives that come later. And the interesting point about it is that when we do this, the value doesn't change in the end, but this order of doing these operations changes the values that we multiply, basically, and the number of operations that we have. Let me find this one. What an integral. There was some resource that I wanted to show. Was stack exchange reverse mode. This one. So I'll send a link to it, and you can take a look at it in more detail. But the idea is that here's the differentiation, and here is the forward mode. So we start with the first one, and then we open up the later ones, and the reverse mode when we have the final one, and we open up the older ones as we go. And here it turns out that the number of multiplications is different that we have to do because of the shapes of the matrices that we multiply. And in short, what this amounts to is that one of the modes is good for a case where there are more inputs than outputs, and the other one is good for when there are more outputs than inputs. The one we have, the situation that we have in training neural networks is always that we have a lot of inputs, we have a lot of weights, W1, W2, W3, etc., and we get some loss. So this is a function of many inputs and one output. And in this case, reverse mode is the one that works the best. It has the least amount of computations, because basically in one sweep, we go through everything, all the derivatives with respect to the derivative of this with respect to all inputs. Forward mode differentiation works best when we have one input and many outputs. I'm not sure it would be loss one, loss two. I haven't seen many cases of that, but that's kind of exactly what we have with curves, right? We have t, which maps to x, y, z, whatever, many values. So conceptually, both the forward and the reverse would give us the answer, but if you want to make it super optimized, you could use forward mode differentiation for taking those derivatives that we were talking about before for our curve functions. That should be theoretically faster. And I made a point here of why can't we just take a gradient of the curve. So if you defined some curve, in this case a circle, and you try to take a gradient of the circle and run this, we have an error that the gradient is only defined for scalar output functions, and the output had shape too. So that's the problem, right? We have t and the output is x and y. So the function that we're trying to differentiate has two outputs. And the only thing that deep learning libraries can handle is when we have one output, one loss. So if you go to the gradient definition, it will say that basically the gradient is also used to measure how a scalar field changes. Okay, sorry, not this one. Scalar value. Anyways, the gradient is only the derivative that is defined for a scalar valued function. So it can take many inputs. It can take a vector or a matrix or any tensor of inputs, but the value of the function is always a scalar. So we can't use gradient for calculating the derivatives. It's not mathematically correct. But we do take the derivative. And in JAX, the derivatives can be taken by, in this case, it would be a Jacobian. So we can take the Jacobian using forward or reverse mode. We can also take, as they say, the Jacobian vector product. And here I have two implementations. So one is taking the Jacobian vector product, and the other one takes the full Jacobian using reverse mode differentiation. The results are the same. The difference is that this Jacobian could be used when we have other types of functions where we'd have many inputs, x1 and x2 and x3 mapped to many outputs, output 1, output 2, output 3, and we'd get so in total like some m by n. And we'd get with this Jacobian, we'd get, when we take the derivatives, we'd get an m by n matrix. In our case, we only have one input and 3 outputs. If we take a Jacobian, it would be 1 by n. So it doesn't matter if we take the Jacobian or the JVP, the Jacobian vector product. I guess I didn't explain to you what the dimension of Jacobian vector product is, though. I can go into that, but first, please tell me if you're totally lost or not. Does somebody have questions to the stuff that I've covered so far?
I think we have more or less covered the Jacobian matrix, that its dimensionality is the number of inputs times the number of outputs.
Okay, so the difference between the Jacobian vector product and the vector Jacobian product, right? The JVP and the VJP is their dimensionality. So one is calculating, one has basically, I'm not sure which one has which, but okay, we can derive it now. Basically, one has this and the other has this. So one takes the derivative with respect to all inputs, and the other one takes the derivatives for one input with many outputs. So they have different dimensions. In our case, JVP is the one we need. I think, yeah, 1 by n. This is the one we need. So we have one input, many outputs. And this is exactly what it gives. So we could take that, or we could take the full Jacobian, which in our case would still be 1 over n. So that kind of doesn't matter, and all cases work. The only difference in code is that when you take the JVP, that's just the technicality of how Jacobian vector products are computed, that you have to pass in the value of where you want to compute the derivative at initially, and you have to pass in a vector of where you want to calculate the derivative, the Jacobian vector product on. So if you go to the JAX documentation, it has this explanation that JVP, the Jacobian vector product, is a function that takes x and some vector and returns the value of x and the derivative times this vector. So this is a Jacobian vector product. So this derivative is a Jacobian and this is a vector. So we need to pass in some vector. And if we only care about the actual value of the derivative, then the vector is 1. So this is just, you have to write some more code and understand how JVPs work if you want to compute it this way. But you can also just don't care and do the way I did it with the Jacobian here. So then the Gauss map becomes, we take the derivative of the curve and we do a derivative at t divided by the norm of the derivative at t. And that's the whole function that we then use and calculate its length with the integration. So that was a lot of theory. In the end, we have some shapes here, some Archimedean spiral, log spiral, helix, and circle. I can show later how these look. You know how circle looks, and I have a picture here how helix looks. Is this basically also a spiral that goes in the direction of t, like a circle, but we also change the move in space. And we'd like to calculate the Grassmannian length of all these. And we can see that the lengths are different for all of them, except for the circles with different radii. Radius 2 and radius 5 have the same Grassmannian length of 2 pi. And I have no idea how we can verify this. I guess the authors of the course have the right values for these, but I couldn't find a Grassmannian length calculator anywhere I searched for. So I guess we have to think about it, and I have some questions to it. The main question is, if you think of a helix, so value 3 and value 4 are different helixes. One is with radius 0.5, the other one is with radius 2. So the first interesting point from here is that helix with a different radius has a different Grassmannian length. This is something that is not intuitive to me. If you look at this thing, if you change its radius, it says that its Grassmannian length changes. And that's kind of like, I have no idea how to wrap my mind about this. If anyone has an idea.
Maybe Raul can comment this.
Yeah, not really. The only very, very trivial case is that, of course, for a straight line, the Grassmannian length should be 0. That's clear, right?
Yes, I tested this. So we have a line, 2x plus 5 Grassmannian length of a line. However much pi we have.
In the Gauss map, it will always be the same vector all the time. So the length of that in the unit sphere will be 0. About the helix of different radius, I guess, well, I don't know. The vectors that you are putting in the sphere will be, well, it seems that if the helix has largest radius, the vectors that you will be putting in the Gauss map in the sphere will be, maybe will be occupying a larger circle in the Gauss map. No? Well, I don't really know.
It is true that if you look at this, a helix with a bigger radius has a bigger Grassmannian length. And that is kind of weird because there's this paper on which our, I guess,
I think the way to see this would be to really visualize, because you can visualize, because if your curve is in 3D, your vectors will have 3 components, and you can really visualize the Grassmannian on the unit sphere, right? So you can really see how these vectors, at least for curves in 3D, you can really visualize how the Grassmannian curve looks like, and then we can have a better intuition what these points do. Because it's clear, for a straight line, it's always the same vector, so the length of that should be 0. But for helix and spheres, sorry, for helix and circles, I think it would be very nice if this could be visualized, because it can be visualized, the Grassmannian.
Oh, that's a good idea. I should have done that. Maybe if we have time in the end, we can try to do that. But all right, for now, I guess the whole idea is that we can't. I don't know how to verify the calculation of the Grassmannian length for all these cases, but for cases that we do know about, like the line and the circle, they do agree with the theory. And there's this part that I'm confused about of why a helix with different radii would have a different Grassmannian length.
For the sphere, for the circle, it's easy to understand why it has to be 2 pi, because you will always have vectors pointing in opposite directions. So you really, the Grassmannian curve for a circle should be a full circle also on the sphere. Should be like one of these, how they call it, major circles or great circles in the sphere, right? And then if it's a major circle or a great circle on the surface of the Earth, you have the same length, right? Because it's a great circle. So regardless if the original circle is small or large, in the Gauss map, you will always have a great circle. And the length of that is 2 pi, always, right?
Is it the same for a helix?
What?
Is it the same for the helix?
For the helix, you mean?
Mm-hmm.
For the helix, it must be something different because this, no, for the helix, no. I wonder what is the Grassmannian curve for the helix, but it cannot be a great circle. Maybe it's a circle, but not a great circle, you know. But I don't even think it's a circle on the Grassmannian. But I think maybe if you don't have time to do it today, it would be nice if you share it in a Slack. Maybe this plot, maybe today or tomorrow, whenever you have time, I think would be nice.
Mm-hmm. Yeah. I'll do that then. Okay, yeah, I mean, it's obvious that it looks the same way if we change the radius or not. Okay. The point I also wanted to make about this is that the most confusing part about it is not just that the Grassmannian length changes for different helixes, but the fact that for a bigger radius, the Grassmannian length is bigger. Why that is confusing to me is because in this paper where basically our assignment takes this picture from, and the whole idea of using Grassmannian length for neural nets is this paper called Exponential Expressivity in Deep Neural Networks Through Transient Chaos. These guys make extremely complicated stuff here with Riemannian geometry, mean field theory of high dimensional chaos, and et cetera, et cetera. But what they show here is the intuition that, is it here? It's here. Basically, they show that Grassmannian length is computed via the length of the, I mean, that makes sense. It's computed via the length of the original curve and also a value that is inversely related to the radius. Basically, they have this thing, this oscillating circle. If you think about a curve and a point on this curve, if you take the velocity, you get this vector, right? If you take another derivative, you get the acceleration vector. And having an acceleration vector and velocity vector, you can basically derive a circle with some radius. And the bigger the curve, like, look at this place, at this point. We're not too curvy. We are curving a little bit, but not too much. And our radius is big. But think about this point. In this point, we curve a lot. Like look at this angle. We curve a lot. And if we draw this kind of circle here, the radius would be tiny. So the radius is inversely related to the curve, which to me sounds like the bigger the radius, the less curvy we are. So it's very confusing to me why the Grassmannian length that I calculated is bigger for a bigger helix. I mean, my implementation looks correct from like mathematically, but it just doesn't make sense to me. So I guess Raul and Tambet, you're right that it's good to visualize it. So I'll do that, and um, I'll send it in Slack, and we'll see if it explains anything. And before,
I wanted to ask. I
Yeah,
wanted
go
to
on.
ask if any of the students did the homework already, and did you get the same numbers? Can somebody confirm those numbers?
If not, it's all right. I can publish these numbers in Slack as well. And we'll
I
see
did,
if,
and I got the same numbers.
Oh, okay. Okay.
But yeah, I didn't get to the confusing helix part. I just verified that it worked as expected with a circle and line.
Yeah, okay. Then I guess the only thing we could do is to draw this, the Grassmannian itself, the unit circle, and see for different shapes, for different helixes, and see how it looks. Maybe that will give us some insight. But for now, we can move on if you'd like. Oh, yeah?
I wanted to make a quick comment about the code. Can you show me the functions? Yes. I had the same dilemma of whether I should be using the JVP or the Jacobian. I think the Jacobian forward would be more reasonable to use in this case because we have one input and two outputs.
Yep.
So, and
I think that's what I did, and I just was Jack forward faster.
No, it was slower, which is really confusing to me. Which is really confusing to me because maybe you can go up a little bit. First thing, I think what you can do in your code, this gradient function, you can create it outside of the cos map function because you don't need to recreate it every time. You just create it once.
Oh, you mean this?
Yeah, this line, you can just move it outside of the...
oh, yeah.
Yeah, there. Then when you calculate the gradient function at certain place t, then you don't need to calculate the Jacobian again and again. You just
exactly. Okay, that makes sense. The only place where it is needed is if you take if you use the JVP, because if you use the JVP, you can't create a derivative function and then just give it values. You have to when you compute the JVP, you have to pass it a value.
Exactly.
Which makes it slower.
The JVP calculates the derivative or Jacobian at certain point, but the Jacobian forward produces a function that calculates it for you, and you can use this function later. And it was very confusing me. This Jacobian vector product, it also does this useless product with a vector, which we don't really care about. We just pass vector of 1 into it. Yes, there. So I was expecting that first the JVP has to calculate the derivatives, then it has to do the useless vector product, but it's still faster than the other function that just calculates the derivatives, and which does it in advance and later doesn't need to calculate them again. So I tried putting this at JIT in front of the functions so that they will be compiled, but still JVP is still faster. So maybe it's just better optimized because I think when I read the documentation, the way they explain it is that you don't calculate the full Jacobian matrix because you do the vector product first. You are always working with vectors, not with matrices.
Yep.
And it's more used and maybe therefore more optimized. But the other comment I wanted to make about your code is in the other place, when you integrate, when you do the integration, the curve length, there you use the Jacobian reverse again. You could replace this with a JVP as well. And then it makes it a little bit faster again. Because in the instructions, they said that you can get away with just applying JVP twice. And that's one place.
Yep. And here the other. Yeah, that makes sense. I didn't like the JVP because it would have to, like I had to pass these in and it looked just ugly. And I thought I didn't time it. So that was, then it makes sense that JVP works better since it's faster.
Yeah, it was surprising to me. I see no reason why it should be working faster, because it does some useless functions which are not really necessary, but in practice it does work faster. A little bit, not much.
I mean, the JVP, I'm sorry, the Jacobian is calculated through JVPs as well, or VJPs, I'm not sure. Yeah, I mean, it depends, I guess, on the input. But here, if you see the source code of JAX for Jacobian forward, I mean, Jacobian forwards is with JVP and Jacobian reverse is with VJPs. But maybe the way it does some additional stuff on top. Like it has to, it does the VMAP, right? So maybe just setting up this loop for going through all the dimensions, in which case, in our case, there is just one. But maybe just setting up these loops and doing some, like it does a lot of stuff just to compute the actual matrix, and we don't really need the actual matrix. We only need one row. And maybe that adds the complexity to this Jacobian function, although the output is still one row. What if, how fast is it going to be? I'm just curious. If we do JVP here, and we take this, is that correct? And then we take this. Okay. Tuple, okay. I have to fix stuff here. All right, we'll do it later then. Thanks for the comments about the code though. Okay, so the final thing is a question on applying what we've done to neural nets and where does it break. So the question is, we can apply the Grassmannian length function to a neural net when we have activation functions that are differentiable, like sigmoid and 10H. But the problem comes with ReLU. When we do deep learning, we don't care that ReLU is like has some problems with differentiation. But in this case, they say ReLU would break everything, would break the Grassmannian length and give nonsensical results. And what is the intuition of that? So I guess there should be a deeper intuition. But if you just think about the derivative of ReLU, it is zero in in like half of the space, right? If we don't even start to think about the 0 point where the derivative is not defined, the derivative of ReLU is zero in half of the space. And when we compute the Gauss map, we divide by the norm of the derivatives. So we kind of assume that this is not zero. And here we do say, we assume that v of theta is not 0 everywhere along the curve. So we basically have to rely on the assumption that our derivatives are not 0 everywhere. So basically that we change, that we do move around the curve. Otherwise, it's not a curve, right? But ReLU has the 0 derivative in half of the space, which means we're not kind of moving in the function space. And it just breaks this Gauss map. It makes it not a number if we try to calculate it. And that's where everything goes wrong. And then in the end, I think like the way Jack's handle is that if we take a ReLU, of course, I mean, grad ReLU of 0, they say it's 0, which is just a convention. ReLU. Oh, maybe I need this. Yeah. Anyways, the gradient of ReLU is 0. So if we take the Grassmannian length of ReLU, it says it's 0, but I think it's just that it handles stuff, because if we take the Gauss map of ReLU and evaluate it at let's say 2.2 pi, it is 1. Oh, that's interesting. What about 0? Okay, 0 is not a number. For 0, Gauss map breaks. So Gauss map is not defined for basically values smaller than 0. I'm not sure like why in the end, if we take the length of this, like the integral of this, that it doesn't just break and gives us 0. This is kind of some coding magic here for me. But we shouldn't treat this 0 result, I think, the way we treat the line Grassmannian length. And I guess that's where the nonsensical result comes in. So that's the only thing mathematically that bothers me with ReLU. And intuitively, I can't really explain it that well. Like if we think about ReLU, why does it break Grassmannian length? I mean, if the derivative is 0 of the first derivative, right? When we take the Gauss map, it means that here our values would be nothing, right? It would be just a dot, or like just a point. And I'm not sure. I'm not sure what it does. Kind of sounds similar to a line. If we take a line, a derivative of a line would be, it wouldn't be a 0 though.
I think it probably introduces a jump because, first of all, to be defined mathematically, yes, you need the derivative to be well defined. Otherwise, if it's, that is not well defined. At the ReLU, at the 0 point, is not that the derivative is 0, it simply is not well defined even, right? And I think if you take the ReLU as a curve, then and you will compute, imagine you can ignore just the point in which is not derivative. It is not derivable at 0. Imagine you discretize it, but you forget that point, or it's not appear in the discretization. Then I think you will have like 2 straight lines, so piecewise lines, so 2 straight lines. I think they will correspond to 2 points in the sphere, and there is a jump. So how can you compute the length of something that you know is not? Let's say you have a continuous curve in the original space. You will have, I think, usually a continuous curve in the Grassmannian on the unit sphere. You know, it will be distorted, normalized, whatever, but a continuous curve maps to a continuous curve. But here you have a piecewise line like the ReLU with 2 pieces, and here there is not derivative is not well defined. I think the Grassmannian would correspond to 2 points, to 2 vectors that are far away.
Yeah, that makes sense.
I think. And then what is the length between 2 points? I mean, you need something to integrate between them. You need the length of a curve, but the length of 2 points is not well defined, right? So I think it's problematic. But what I have is more a conceptual doubt, which is all this of the Grassmannian length is defined for curves. So for a neural network, what is the relation? The relation is that we will take, now the curve is what? Is the activation function. But that per se, it's just the activation function, right? So I guess we will need to relate it to where in the activation function is being called with input. No, what I'm lacking is to see the connection of how the neural network we can understanding as a curve, so that these concepts tell us some measure of nonlinearity. We saw that a straight line gives Grassmannian length 0, so we can take maybe then the Grassmannian length is some indicator of nonlinearity somehow, you know, in some sense. But here, when we apply it to the activation function, okay, we can interpret that as a curve, and we can compute the Grassmannian length, maybe not for ReLU, but okay, for other activation functions maybe. But how that connects to the nonlinearity of a neural network? How can we link the neural network with a curve such that the Grassmannian length of the curve tell us something about the nonlinearity of the neural network? That is perhaps what is not explicitly mentioned so far.
I think what yeah, Tom, go on.
The way I would think about this is that we have a neural network that ends with a loss, and now we can integrate over one of the inputs. Like let's say 1 pixel from the input image, and we integrate over the values of that 1 pixel, and the output that we are measuring is the loss of the network, and then we can calculate the Grassmannian length of that curve.
So the curve that we associate to the neural network would be kind of the curve described by changing one input, how the loss function is modified by moving that input, so to say.
Yes. The other option would be that we integrate over one weight. But it seems to me that when the question is how nonlinear is the network, then it would make more sense to integrate over the input, it seems to me.
Mm-hmm.
And of course, instead of loss, you could be using also, I don't know, a probability outputted by the network, or in case of regression, the regression output, prediction output of the network. But maybe loss is, then it also takes into account the non-linearities of the loss function itself. So maybe it's even better. Or it depends what you want to measure. If you want to measure the non-linearity of between the input and the output, then I guess what you should measure is by integrating over one input value, and output is the, let's say, prediction of the network.
Because the curve can be, yeah, I think, yeah, one can use the loss, but maybe before the loss also would make sense, because if you have the output layer several nodes, you can understand the curve as being as dimensional as the number of outputs, no?
Yes, indeed. If you have multiple outputs, let's say probabilities of multiple classes, or even the logics before you convert them into probabilities, yeah, you could apply it there.
The other way to think about it, I'm not sure it's exactly that follows this paper, but anyways, they use Grassmannian length here in this paper to understand how a manifold or a point or a bunch of points would go through a network. And basically they show that deep networks with large weights would have the curve, the original manifold, a circle, transformed into a more wiggly circle. And then the Grassmannian length of this wiggly circle would be high. They don't say, like, the Grassmannian length here is just Grassmannian length with depth. I mean, thus linear expansion increases length, decrease curvature by maintaining. So they don't fully expand on the notion of Grassmannian length. They don't expand that very well. But the way they compute, what they compute it with respect to, I think, is that they take T as the layer, So the T becomes discrete. It becomes the layer, and then the activations of the neural network at that layer become the values of the curve, and that's how they treat this with the Grassmannian length. So again, our T, our time, is the layer, and our position of the curve, its state at this time, is the activation, which depends on the weight, depends on the previous activation, and the activation function.
I mean, as a curve, I think you can just take the activations at any layer, so to say, to define your curve. We discussed before taking the output layer or before that, and I guess you can take it at any layer and consider that as a curve. But the time or the index where you are, or the parameter in the curve, I think that should be something else, because it cannot be the index of the layer, I think. I think the index of the layer defines, let's say, different curves, if you wish. And you can compute this for curves defined with the output as the first layer, the 10th layer. But the curve itself, how it's parameterized, or the time, I think should be something else.
You cannot take a derivative with respect to the index of the layer.
Mm-hmm.
That is true.
Yeah. I think it makes more sense that there is something with the input, as Tambet said in the beginning, something with or the input, or maybe only changing.
Changing only one pixel, that seems very limiting as well.
Mm-hmm.
Or maybe you can do it for all the pixels one by one, average. and I don't know, average or some of these.
Mm-hmm.
Projected curve. So I feel like they don't explain very well what the curve is here. Theta. Oh, okay. The extrinsic curvature of the Dipper parameterization. Maybe they use a weight for the curvature, for the time. But yeah, yesterday I was trying to understand this paper, and there's a video I can share a link later, where the author just does a talk, makes a quick talk, like it's 25 minutes, and it includes stuff from this paper. It doesn't explain Grassmannian length and intuition behind it that well, but and it doesn't have a clear answer to the question we have of what exactly, like how do we treat, like how do we map a neural network to a curve, but it bounces around about that, and maybe you can have an idea of what they mean if you watch that, and if I rewatch that again. But yeah, I guess for ReLU we have some intuition now. That it's, as Raul said, it jumps around in space, so it's not monotonous anymore, and then the distances are not well defined for points in space that are not on a line. So that's why we can't do it for ReLUs. And in this paper, they also didn't do it for ReLUs. In the video, I'm not sure they mentioned here. Oh, they do. That it's a sigmoidal or 10H activations that they use. Otherwise, I think they wouldn't be able to compute all this. So I think this is it from my side. I have already a list of resources that I'll send to you. I don't still have a clear intuition, as I said, of why, how exactly we would apply this to neural nets. So if anyone gets this intuition later, please tell me. I guess everyone will be interested as well.
Yeah, the simplest straightforward case would be to integrate over one input and then measure the Grassmannian length of the output of the network, like multiple neurons or one neuron, or however you please. And indeed, that only works with the tanh and sigmoid activation functions, and it's probably quite expensive. And I was wondering, what do we even learn about that? How nonlinear the neural network is? Is this a good measure? How nonlinear something is? I don't know if Raul, you have some intuition.
When I read that this is useful for measuring nonlinearity, the first thought I thought is that the usual way to measure if something is linear or not is the following. You probe your system with one input, you get some result. You probe the system with another input, you obtain a different result. And then somehow you try to probe the system with a combination of the two inputs, and then you see if the output is also a combination of the outputs you obtained before when you show only one input at a time. That's kind of the usual definition of linearity or not, whether a linear combination of inputs produce an output, which is also the linear combination of the individual outputs that you obtain when you probe the system one by one. That's the usual definition of if a system is linear or not linear. But I don't know here what would be the meaning of combination in the input side. If we have a well-defined operation to say, I sum up two inputs, I want to see if the output is also the sum of outputs, of individual outputs, then you need to define well what does it mean to sum inputs in the input space. If that operation is well defined, then you can always look for that deviation, for how much the output for a combination of inputs deviates from the summation or the combination of the outputs you obtain individually. Any measure of deviance of that could be a measure of how nonlinear your input, your function is, so to say.
What I mean,
yeah.
What I mean is the more non-linearity always better.
That's what they claim, that the more nonlinear the better.
Nope. They basically show that there is a mode where the network learns, or not learns, they don't talk about learning, where the network represents stuff the best. There's the chaos mode and the opposite, I guess, peace or something mode, where the network would, you would give some inputs to the network, like 2 different points. And you look at not the output length, not this, you look at the correlations between these 2 points as they go through the network deeper and deeper. So the correlation for different weights, what defines everything is the depth and the standard deviation of where the weights were drawn from.
Because I mean, what I think is at play here is that I think there always is a tension between the fact that a neural network, we wanted to have some robustness. To very similar inputs, you still want to classify the same, right? And at the same time, it has to do some folding. It has to take inputs that are very, very different into the same class also. So you want a dog, and a dog with a small modification, you have to send this to the same output, so to say. But at the same time, if you have a big dog and a small dog, the pixel-wise, they look very different, and still it has to be folded, this input, they have to be routed to the same output, right? So in a sense, I think the network has to be nonlinear because it has to send things that are very far away to the same location. And at the same time, yeah, if the input space is not well ordered, so to say, the input space, you know, the different classes are mingled, so to say, in the input space, then it has to really unfold these things so that at the last layer, everything is linearly separable in some sense, no? Mm-hmm. So it seems that it has to be nonlinear to some degree, but at the same time, it has to be smooth so that a few pixels away still is the same. No? So I think there is always this tension between trying to be linear in some sense that nearby inputs are mapped to nearby outputs. Actually, it has to be continuous, at least, because all the operations that we do are kind of continuous. But at the same time, it has to fold things so that things that are far away in input, they are folded so that they will appear near in the final layers. Like if you think about exclusive OR, it has to be nonlinear because it has to send 2 points that are in 2 opposite diagonals. It has to fold them so they appear in the same location so that you can put a hyperplane in the hidden layer to make an exclusive OR, for example. So I don't know. I from the intuition point of seems that it has to be this tension always. It has to be nonlinear to some degree. But how much it is optimal, I guess it depends on the task. For some tasks, it has to do a lot of folding, I guess, to bring points that are very far away in input to bring them together in the output. For other tasks, maybe it doesn't have to do so much folding. I guess it really depends on the task and on the data. And maybe this is also useful in some sense because I remember in the very beginning with adversarial examples, some people said, this is due to the network operating in a very linear regime after all. So maybe this is one way to quantify how linear or non-linear is the network. But it seems to me that the non-linearity that it has to learn or how non-linear a network should be, it really depends on the job it has to do with putting inputs that are far away together, or at least in one side of the hyperplane or the other.
So when I read this abstract that you're showing right now, they are saying that non-linearity of the network grows with depth, but not so much with width. And that makes sense because the more layers you have, the more non-linearities you have. But they say it grows exponentially. So maybe the exponentially is the new thing that.
Yes, they're just trying to
not,
show
obvious.
Yeah, because there is this theorem of universal approximation that even one layer neural network is already a universal function approximator. And then the question is, of course, how many neurons do you need to approximate a certain function? And basically they show that for the same number of neurons, you can, with the deeper layer, with the deeper network, you can approximate an exponentially more complex function than with or basically you need an exponentially smaller number of neurons to approximate the same function than if you just grow in width. And that's, I guess, the new thing. And also the new thing is this idea, I mean, they say they formalize and quantitatively demonstrate this idea that deep nets with all the expanding of space by transformations and then collapsing it with the nonlinearities, that they can disentangle highly curved manifolds. Basically, if like all our inputs, like images, are highly curved manifolds, that's how we can think of them. So if we want to classify them, they need to be linear. And then what these networks do is that they disentangle the manifolds into linear things and also make, as Raul said, those that should be classified together closer, so they can track the space around them, but they expand the space between different classes. So they just basically show how it should look like. And I mean, this visualization is just PCA 3 first components of some large input. But it kind of shows that that's kind of what, I mean, that's the opposite of what's happening, I guess. If we take in a circle, it gets fused into this. But I guess if we would get some kind of input like that, it would disentangle it.
Because at the end, the only thing at the end, we put a linear operator at the end, right? At the end, we separate with hyperplane. So at the end, the problem has to become linearly separable in the last layers, in some sense. So the only way is if you start with two manifolds corresponding to two classes, and these are very entangled, like some, I don't know, something like this, you cannot put a hyperplane then. So the networks the layers have to somehow try to make that separation as linear as possible. And that is what they mean by flattening, I think, the manifold. But what I would put into question is that the manifold is preserved actually across layers. If you use a ReLU, I think you might start with a smooth manifold, but at the end, I think I discussed this with Antti, and at some point, I think we think that you might start with a smooth manifold, but when you have ReLUs, you destroy the manifold. You cannot break it because the operations are continuous, but you don't end up with a smooth manifold anymore. So this manifold view is nice, but I really wonder if with ReLU it holds true, because I don't think you end up having smooth manifolds anymore.
Mm-hmm. I think we have to wrap it up now. Thanks a lot for Mikita for a well-prepared presentation. And in hindsight, I feel a little bit sorry for Tarun, who had like a 50-point homework when others have 20 and 25-point homework. I should have split the first homework into two, but that's how it went. So I guess we are finished. And thanks everybody, and thanks to Raul for insightful comments.